Hi folks, welcome back. So today I want to talk to you about another paper from the very recently concluded USENIX annual technical conference. And this paper talks about how to use a language-based abstraction to write programs for trusted execution environments. This work was done by researchers at EPFL, Switzerland. The basic problem we're trying to attack is an old and well understood one. The problem is that software today is vulnerable to a wide variety of flaws, and these flaws can allow attackers to steal private data such as encryption keys and so on. To deal with these attacks, the processor vendors introduced the idea of a trusted execution environment. The idea was to create a hardware-based isolation mechanism that encrypts memory and isolates program execution and state from all other software, the operating system, the virtual machine monitor, firmware, and so on. In fact, even from people with physical access to the machine. Intel's implementation of this idea is called SGX, and it's based on partitioning hardware and software into two domains. A trusted domain, which is small and well-defined, and the remainder of the system, which is your usual execution environment, is considered untrusted. SGX, when it first appeared, seemed to have addressed a lot of problems, but its adoption has been pretty slow. One of the major reasons for that slow adoption has been the difficulty of programming trusted execution environments. Right now, they don't have any good abstraction that lets you take full advantage of them. You essentially have to understand your application at a deep level and then refactor it into these two parts, the trusted part and the untrusted part. Before we get into the abstraction being proposed in this paper, let's look at SGX in a little bit more detail. SGX stands for Software God Extension, and it allows the user to create enclaves. An enclave is simply a contiguous region of memory that is protected from outside access and modification, even from the operating system or other privileged software. The trust model is asymmetric. The enclave has access to all memory, but untrusted code cannot access or modify enclave memory. In addition to this memory restriction, we also have restrictions on how control of execution can be transferred back and forth, and this can only happen at pre-approved entry points. The way the CPU ensures memory protection within an enclave is via encryption. When data goes out of a cache line into main memory, it is encrypted. And when it comes in from main memory into the CPU cache, it gets decrypted. Obviously, since you're doing all this encryption and decryption at runtime, this affects memory bandwidth and reduces it by a substantial factor. Now, the authors do recognize that due to a spate of recently published attacks such as Meltdown and Spectre, which utilize side channels to read data out of even CPU cache lines, SGX is essentially broken currently. But the point of this paper is to propose a good high-level programming abstraction that can be used to program trusted execution environments in general, even though Intel's specific implementation is known to have several vulnerabilities. So coming back to some of the details of SGX, you can, when setting up an enclave, tell it how many threads can execute within that enclave. And user-level software uses these special instructions to transfer control of execution to the enclave. And then the enclave can use these special instructions to transfer control back out to untrusted code. And to bootstrap this chain of trust, SGX relies on a mechanism called remote attestation, where we have to take a measurement, which is essentially a signed hash, of the software that we load into an enclave before it executes. This signed hash is what prevents us from loading arbitrary untrusted code into an enclave. The maximum size of an enclave is 128 megabytes. So this means we do have to put some thought into the total size of the code we put inside one. One of the major problems with enclaves is that there is a pretty big performance penalty to transferring control back and forth between the trusted and untrusted modes. They are about an order of magnitude more expensive than a system call. How would you actually build a secure system on top of this SGX mechanism or with any trusted execution environment in general? One very simple brute force approach is to take your entire application and put it into the enclave. This obviously has a lot of drawbacks. Your trusted computing base is huge. You actually want to put only a small trusted subset of your application into the enclave. So then what you could do is you could split your application into trusted and untrusted parts. But that does not come for free. That means you need to understand your application at a deep level and actually refactor it. In this paper, the authors are presenting an abstraction that lets you conveniently program trusted execution environments built on top of the Go programming language. If you're not already familiar with Go, one of the central abstractions in Go is a Go routine, which is essentially a user-level thread executing a closure. The thing to remember is that Go routines communicate and synchronize using channels, not shared memory. The authors are introducing one new keyword to the Go programming language, and this is also their new abstraction, and that keyword is Go secure. In regular Go programs, you start off a Go routine with the keyword Go followed by the name of your closure. This new Go secure mechanism works very similar to that. It still fires off your closure in a new thread, but does so within the enclave, hence the Go secure name. Here we see a simple toy application that generates a secret key and then encrypts something with that secret key. Here we see a Go secure call to a method to create the secret key, which means that this entire function is executed within the enclave. Note that the secret key is generated and stays within the enclave. Similarly, this call to encrypt something with the secret key again is executed entirely within the enclave. The secret key never leaves the enclave. Only the encrypted data comes out. Note that all communication between the trusted enclave and the untrusted code outside is happening via Go channels. For example, here to encrypt, you pass in as a channel the bytes that you want to encrypt, and then you get out of that channel the encrypted data. Now, if you've programmed in Go, this is actually very idiomatic programming. This is how you're supposed to program in Go, by passing messages via channels. So the cognitive overhead of this abstraction to a regular Go programmer is very low. This is a very natural extension to the language that naturally accommodates how to do computation within trusted execution environments. A very nice side effect of this is that the compiler can use the Go secure keyword to figure out how to partition the code into trusted and untrusted domains. And in fact, these two domains need not be disjoint. They could actually share code, for example, common library routines like println and so on. So how does memory isolation work with this model? The two domains are completely separated. Each domain has its entirely distinct set of memory, which has all its symbols and data and global variables and so on. And these channels that are used to send data back and forth between the trusted environment and the untrusted environment, while they look like regular Go channels to the programmer, under the covers they are slightly different. They are called cross-domain channels, and they have deep copy semantics. They will never pass pointers between trusted and untrusted code. If you pass in a parameter that is a pointer, the runtime will make a deep copy of that data before passing it into the enclave, and then another deep copy before passing it back to the untrusted side. Similarly, function arguments passed into the trusted environment are also deep copied. All this deep copying ensures that code running inside the enclave cannot inadvertently write secret data to an untrusted memory location. Remember that code running in the enclave can access all of memory, even untrusted memory. This way, we know that all data that goes in and out of an enclave has to be explicitly sent or received over a cross-domain channel. Now, as we'll see in some benchmarks a little bit later, this abstraction gives you a pretty big performance improvement compared to the usual way of programming the SGX enclave. The reason for that is that the control transfers between the two domains now simply become inexpensive typed data transfers over cross-domain channels. You only need to do domain crossings when you're initializing your SGX enclave. Another very pleasing side effect of this abstraction is that since each domain, the trusted and the untrusted one, has its own copy of data, the garbage collector can safely manage each space individually without having to cooperate between the trusted and untrusted parts of the application. Now let's look at how this abstraction was evaluated. First of all, let's look at programmability. The comparison was with the Intel SDK for SGX. And if you look at a Hello World program in that SDK, it weighs in at around 355 lines of code. The reason it is that complex is that programmers have to define all the boilerplate for code that lives in the enclave and how it communicates with untrusted code outside the enclave. On the other hand, for the abstractions proposed here by the authors, a hello world was simply 13 lines. Looking at some other performance microbenchmarks, the latency for a secured Go routine and writing to a private channel was about 5x that of a regular Go routine. However, that was still about 2.5 times better than the latency from a similar program written using the Intel SDK. And the reason again was that the Intel SDK program required a full execution crossing between the two domains. They found that the garbage collector had pretty much no impact on performance. So to conclude, as people have gained experience writing programs on SGX, it looks like the most effective way to do that is to partition your application and have it execute only trusted parts of your application within the trusted execution environment. And that is exactly what this Go Secure abstraction achieves. It treats the enclave as a totally different computing entity. It uses message passing with deep copies, which has the nice advantage of keeping these two memory spaces completely disjoint from each other. Its performance is much better compared to so-called native SGX applications because it avoids expensive cross-domain control transfers. And even though the specific implementation on which this abstraction was currently built, SGX, happens to suffer from vulnerabilities, the abstraction itself shows how to do this for any trusted execution environment in general. So that was a look at GoT, which proposes a Go routine-based abstraction for programming trusted execution environments. I hope you enjoyed that, and I will see you next time. Thank you very much.